Hey, John here. Let's take a closer look at the embedded block RAMs inside the ICE40. Make sure we know how they work, because they actually have two ports. In the project I've done so far that I've aired on YouTube here, I've only really talked about the read port. Let's talk about both of these. A huge thanks to my VIP patrons. Thank you very much for helping support this channel. If you're interested in helping support yourself, go ahead and look at the links in the description below this video on YouTube. And of course, always like and subscribe if this helps you in any way. Even if it's a laugh, there's value, right? Okay, so here we go. The embedded block RAM. This is only true about the ICE40 family of chips, the way their block RAMs work in there. Every time you've got an FPGA and it has block RAMs, they all might work a little bit differently. And of course, that's why we have different FPGAs, different vendors. That's how they differentiate themselves. Now, the ICE40 calls these things dual-ported block RAMs, but what you really have here is one port can only be read and the other port can only be written. Okay? Now, it's interesting to see that, when you're writing, you have to give it a clock, and it can either be high or low. That's a configuration option. And when you're reading it, you have to give it a clock, which can be high or low. You have to give it an option when you configure it. And ultimately, that means that this is synchronous. And recently, I've been talking about synchronous and asynchronous bus protocols. Well, now we know why. If we want to read from this memory block, and we have an address going into it, and we enable it and so on, we can send it one or more clocks, and it doesn't matter how many clocks we send it in here. If the read address is stable, we'll just get the same value over the course of time. Now, in theory, the same thing is true with writing. If you have the write enabled and you're clocking it away and you have a stable, address, and the data is stable, you're just saving the same thing into the same place over and over again, and there's really nothing wrong with that. You could let it run this way, and on the Project Nouveau, I do that for the ROM memory when the thing boots. I talked about that earlier on in the series where I talk about that in detail. And you can continue to do it that way if you really want. You just have to make sure that if you're going to give it a write clock, that you observe the setup and hold times on all these other signals in here. And that's where synchronous stuff starts coming into play. I don't want to beat that too much, but I want to point out that what we're going to talk about today is synchronized data that comes from a CPU that I talked about in the last video that I did on my channel when I created a synchronized version of the Z80, the S180 CPU. All right, so I'm in this Nouveau 3 directory here. I've kept like 3 different versions of this Project Nouveau sitting here. There's the original one, there's number 2, number 3, and I'll be talking about this one in upcoming videos where we actually have a video output coming from the FPGA, but that's a different story. First, we need to connect up some memories, all right? So we already talked about these finite state machines and how to synchronize the bus from the CPU in this particular case. And then we can use the control lines to isolate a single clock tick on the phi signal coming from the CPU. And then we can send that to the write enable and or the clock enable over here and tell this chip exactly when and which one of many clock signals that we can send it over the course of time, such that we know the setup and hold times are going to be valid on these data lines up here. So let's look at git log of top.v. So all I've done, is grab the data or the source code from the last video and made some changes. See where it says refresh from Nouveau 2, and then I add an example of the memory. So all we need to do is look at the differences from here. Minus R this in top.v. I also updated like the readme file and stuff. There's a bunch of noise that would come up in a diff if I did the whole tree, but this is the only ones we really care about. for technically speaking, right? I removed some stuff that is no longer there. It was commented out anyway, just to get rid of it. And that's a comment there. What else do we got? These are comments, these two lines here. For some reason, I changed the comments. So these don't really change, but this one does. I added this line. I said, memory request, block RAM read equals this thing. And then I generate this signal down here. Okay. I also talked about what this, we'll look at this in more context later up here to make sure we understand what this means, because it's using the new code down here, all right? So this is the only thing I've done as far as new stuff that's in the FPGA. And it looks a lot like the ROM that I used to boot my Project Nouveau, but this one has both writing and reading, so you've got this if-else thingy going on down here. So what do we got? I create a memory, a 512-byte memory that's 8 bits per byte, okay? And then I create a write and a read signal using the techniques I discussed last time, using these synchronized pulses that we'll see in the source code. Obviously hadn't changed because they didn't show up in the diffs here. And what else do I have? A read data latch. I latch it into this to hold on to it so that if the block RAM becomes disabled, I have a stable copy of the read data that I can continuously send back to the CPU as long as the CPU bus cycle has asserted the read signal. So this is part of converting the asynchronous bus to the synchronous bus inside the FPGA. This latch here holds on to the last thing that I read out of this memory down here. In fact, there's a line of code that grabs it right there on the negative edge of the CPU clock, which is the one time I want to actually grab the data, and it holds on to it so that the CPU can continuously read this as long as it wants. If something is asserting wait states or anything else in the CPU, no matter what, this will hold it stable, even if I decide to go off and use this block RAM for something else. Now, this circuit doesn't do anything else with it. In theory, we could just continuously drive the read output from this block RAM up here and continuously drive that into the CPU. There's nothing wrong with that. And in fact, that is what I do in the ROM, the original ROM implementation, the naive ROM that has this free running clock that just keeps reading, and any garbage that goes into the address would continuously output here. There's nothing wrong with that. But if I decide to use the RAM for other purposes, like have a time division multiplexed operation going on, and I'm reading from different bytes and different addresses over the course of time, it'd be nice to be able to hold steady the one byte that the CPU wants, like I said, while I might go off and do something else. Again, that doesn't happen in this design, but I'm thinking ahead, and that was the sort of thing we might want to do. So I'm going to cache the thing that I read for later use. So let's take a look at the top file here that I made changes on in more context. So what are we looking at here? The first thing that was changed is I added this one line here. And what this thing says is when this thing is true, send this thing here, which is that latch I was just going on about, to the data output bus to send it back to my CPU in this particular test app for the block RAM. As you know from previous videos, the D-bus out signal determines whether or not the FPGA should be writing data onto the data bus, sending it back to the CPU. When it's true, it does, from whatever's in this D-bus out register. Otherwise, it floats it, which is what you'd want if the CPU might be off reading memory and doing other things with other peripheral chips when the FPGA is not writing stuff onto the bus. Okay, so this is no change up here. You didn't see it in the diff. But what I've done is I've added one more case here to our one hot case statement down here, a switch that allows me to send data from the BRAM circuit that we're going to look at below, in addition to the other options up here, like the ROM or, GPIO registers and things like that. So over the course of time, as this design adds more things from the FPGA that the CPU can read, I can keep adding more cases in here. And that should not be a problem with performance as long as I maintain this style of design where each one of them is a one-hot bit and it runs everything in parallel. So I don't, in other words, every time adding another option, another theme that I could write out to the CPU on demand, it doesn't get slower and slower and slower as I add more of these cases in here. All right, so that's why I went over to this one-hot style design. Right. So let's go ahead and see where this thing comes from, which we saw in the diff is down here. So the diff showed this is the only other code, and it's all new code since the last time we were talking about this. So what do we got here? There's my memory. There's these two signals here. There's that latch. Okay, so what are we doing in these signals? Mem-read and mem-write, which I don't think we used in last week's video. What we did is I said you can create these and use them in the future, and the future is now. So they're being created right here. This is true when memrec is true, right? Because they're active low, coming from the CPU. So if mrec is active and read is active, this becomes true. If mrec is active and write is active, then this one becomes true. Just the same as we do with the I/O. And doing it in this technique helps us with the Z80 bus in particular, due to the way interrupt requests are acknowledged using the data bus, and playing games with the reading and writing and memory request signals and M1 and stuff like that. So you have to be careful how you decode the CPU bus on a Z80 to make sure you're not going to get confused and accidentally think that the CPU wants to read from you as an I/O port or a memory device or something like that during an interrupt acknowledge cycle. And this should take care of those cases by including both of these in this expression here, okay? So that's how we end up with these qualified signals. This is memory read, memory write. Nobody else, no other cycle from the CPU would be confused for wanting to read from memory as long as you do it this way, at least on a Z80, okay? So, all right, so when we use those, what we're doing is we're saying when we know that the CPU really wants to read from something, and the address bus has a value. And in this test case, what I'm going to do is I'm going to say if it's greater than 8,000 in hex and less than 8,200, which is 512 bytes in decimal, okay, then I'm going to just send it the data from my block RAM. Now, normally, in the design that I'm using this code on, the Nouveau, I have a giant static RAM chip on there that it would normally read from. But what's going to happen here is that the FPGA is going to jump on the bus instead of letting the static RAM run, and it's going to send its data out instead. Likewise, whenever the CPU wants to write, and the address is in that range, we create a signal that represents that situation, and we allow the FPGA to consume that data during that cycle, which we then use those signals down here, okay? So every time there's a negative edge on phi, we talked about this last time, part of the making the bus synchronous, and the BRAM write signal is true, which is this one there, then we go ahead and save the data from the data bus, the CPU data bus, into the memory, the block RAM, minus 8,000 in hex. Now, the reason we subtract this is because the BRAM goes from 0 to 512, all right, in decimal, or 0 to 200 in hex, okay? And this is going to be an address that has 8,000, 8,200. So what we need to do is subtract this off so that it ends up in, the number, this index into this array of bytes comes out right, all right, because it'll be biased by this huge offset. Okay, and the same thing when we're reading, when we have an edge, we load our latch, which is right here, with the data from the memory at Again, the address from the CPU minus the hex 8000. That's all there is to it. Now, I have this little tester here, and we'll look at that in a minute as to why I felt that was necessary. I'll just leave it in there as a comment in this version of the code, and you can play around with it to your heart's content if you so desire. Now, if we compile it up, let's have a look-see and make sure that everything's fine. I usually do this and look for warnings or errors and stuff like that. We've seen this warning a million times. That's a pretty much stock thing. That's a stock thing. And there you go. You got your one warning about this up here. This one down here from ABC happens all the time. Someday I'll look that up. I'm not sure this matters. It hasn't mattered for anything I've ever done. I've paid a lot of attention to it. Okay, so there's nothing going on there. Just for fun, let's look and see what our numbers are. So it says I could run this up to that fast if I want. Thank God, because we're running it at 18 megahertz. We're well within range. That's all fine and dandy. If we go back here, we can see what kind of utilization we get on the chip. How many LUTs and all that. Where is that? There's a little table in here somewhere. If I can find it. Hello? I thought it was just above this thing. Maybe it's back further. Oh, there it is. So what are you using? We're using 68 out of 7,000 and change LUTs, less than 1% of the chip. That's not bad, because as soon as you do something serious, you might need a few thousand. And then, you need another on hand. What do we got? We're using one of the PLLs, 2 buffers, which I/O pins, and 9 of the block RAMs. And that's not too shocking, because we used 8 of them for the boot ROM to hold that 4K, because each one's a half a K. And I just threw another half K on there now, so that comes out to 9. Everything jives. This all makes sense. Little quick sanity check there. So if we make and program the FPGA, oops. If I can type. Open up our serial port. And hit reset. All right, the thing boots up. Everybody's happy. But does it work? If you think it out, just booting this, using the Z80 Retro, CPM, and the BIOS, and all that other fun stuff. 8-port, whatever is it, address range 8,000 to whatever, is not yet been used in any way. Because remember, the Retro CPM uses this address range to configure and boot up the BIOS, which remains up in this high memory. And we know that CPM, when it runs, it uses the low memory near 0. Nothing's using anything in the middle. And we're smack dab in the middle at 8,000. So in order to test this, what we need to do is to fill and dump out memory around 8,000. So if I say fill 7F80 through 8280 with 26s, and fill that up with data, and then I say dump 7F00 with a little more than that to 8300, and we look and see what got filled in. We can see our 26s here. So what this is I narrate it, fill it with 26s in that address range, and then dump out a bigger address range. So there's garbage here from whatever left it there. Here's the data that I wrote in there, which spans over 8,000 and the 8200, and I filled it all the way up to 8280, which is why there's one extra one right there. Okay, and then we've got garbage up here. So, in a really naive sense, it must be working, right? Well, it would have done this if I did nothing at all, right? Because if it's storing it into and reading it from the static RAM, it would have done this anyway. Which brings us to that hack of a test case in here. If instead we look at C and do this line instead of the one up here, what will happen is I'm not going to read from the block RAM. I'm going to just write the value from the address bus back as if it's data. I'm going to take the least significant 8 bits from the address and send it back as the data. And this is okay because I explained earlier that unless you're going to run an app like Adventure or something that uses all the memory, the retro BIOS, the CPM code, will boot and it'll run fine because it doesn't need that region. And then we can go back with DDT again and have a look-see to see what's happening in there. This will verify that I'm actually reading and using this code here, right? Pretty much definitively. And as I say all this, by the way, I scroll down here to double check this. You know, you might think, you know, all I've done is added code here. And I might have a bus conflict. And what prevents the static RAM in this system design? And I'll let you go look at the schematics and stuff for all the details of that later. But the short of it is, this is the chip enable line that goes back to the static RAM. And normally it's on whenever the memory request is true from the CPU. It wants to talk to memory. Good time to turn on the memory, right? But don't do it if I'm going to write data from the FPGA. So this was designed in from the get-go. Whenever the D-bus out signal is true, and you saw that above, that's how it determines whether it turns its tri-state driver off and on and sends data from the FPGA out. So as long as the FPGA is not writing data to the CPU and the CPU wants memory, then we turn on the static RAM, right? Okay, so a little side note there. You know me, I love to ruin my context with side notes, but it is a good question, and I'm trying to head it off at the pass before I get 100 questions about it in the YouTube comments. So yeah, that's the answer to that question. All right, so what are we doing? We're going to check this version here. So if I say make world and program it and let her go, we're going to see two things here. And this is foreshadowing of another video I ought to do. Look what's happening. While this thing reboots, this is the scrolling. There's DDT running from the last time. And I just reprogrammed the FPGA. And when the FPGA is done, you know, resetting itself and rebooting and everything, it doesn't have any logic in it to boot the CPU. So what I've just done is I've replaced all this circuitry in the FPGA while the CPU is still running. So what was it doing while the CPU was booting, right? Well, it turns out that the clock that goes to the CPU comes from the FPGA. So the clock actually stopped. Then the FPGA was reprogrammed, the FPGA rebooted, and then it restarted the clock that goes back to the CPU again. And because the Z80s are fully static, you can actually run the clock speed at any speed you want, including 0 hertz, and then start it back up again. And because the circuitry didn't change from the perspective of the CPU, it's still running the same program in the same place. So we just, this is talk about a hot swap. We just reprogrammed the FPGA while the CPU was out to lunch and came back to life again. Now I'm going to reboot it to be sure. I mean, I wouldn't count on this always being perfect. It's just a coincidence, because if you think about it, you know, the clock may glitch and the CPU could then fail in some weird way. This is very weird thing to expect to work, but I will observe that I've seen this happen many, many times while playing around, and it happens every time. It's really reliable. So do not get confused if this happens to you, and be careful, because it may actually have caused some weird state or a glitch to cause memory to change its value, or the CPU could foul up. So what I want to do is rerun this display command here. And what we should see is exactly this. So keep in mind, we didn't even restart DDT or anything at all. So here's the garbage that was in the RAM and the data that I wrote in last time. But I'm not reading from the BRAM anymore. I'm reading the address back. So 8800, it's sending me the least significant 8 bits back as a test case. I know I'm reading from that always block in the top code, because there's no way that that would coincidentally happen, even after a reboot, of accidentally creating garbage and resetting everything and all that other fun stuff. It's just not, no, that's not going to happen, okay? Now, to make double sure, and like I said, it is kind of amusing to restart this thing and do a complete hardware swap while the FPGA is on hold. It's obviously a better idea to go ahead and do a full reset on the FPGA and do your test again. Now, the interesting thing here is, because I didn't power cycle it, this should actually still do the same thing, because unless, of course, it touches the RAM in some way during boot, and it very well could have done that. But I happen to know, because I wrote every line of code in the boot in the BIOS startup, it does not do that. So we still see this same pattern. Now, if we fill 70 whatever F, E0 through 82 20 with 44 in hex, okay? And then we do our dump again. I'm going to just play with my mouse here and not have to type that whole thing in again. And we do this. What we're going to see now is, you can see these 44s. Now, I didn't rewrite the whole thing, right? I only went from 7FE0, which starts down here. So again, I can definitely see what's going on. I'm the one who wrote this in here. This is definitely what happened. And I wrote it all the way up to 8220 over this hole, which is now acting very strange. This is not RAM at the moment due to the FPGA design. And on up beyond the end of that, back into the static RAM chip down here. And it all behaves. It does exactly what we expect it to do based on this incredibly strange feature down here. So what do we got here? We have a block RAM. And because they must be edge triggered, I mentioned this before, with the ICE40, the only way to write and read is you must give it a clock, and these clocks are edges. You cannot use an asynchronous signal like write enable, go on, and then come back off to latch in the data on the address that's going into the block RAM over here. It will not do that. Same with reading. To some extent, that's a little bit annoying, but FPGAs are really optimized for synchronous circuits. Period. And that's why we spent the last video talking about making sure we can operate synchronously, even when we're hooked up to an asynchronous processor, by making sure that we have a clean edge and we have these enable signals that bounce on and off for the period, of one cycle duration, so that we can isolate a single clock edge to make this happen and or to make that happen down here. That's why we do this. This is the only way to read and write to a block RAM that's inferred in Verilog. Oops, that's up here. And then compiled with Yosis. Otherwise, it doesn't know how to connect it up to a block RAM. If you don't use an edge here, by the way, let's do this just for fun. I think we got a few minutes here. You'll figure it out right away. Let's say you screw this up. And you say, I'm going to operate asynchronously. And when I'm writing, I'll do that. I mean, logically, this should work. This should work exactly as drawn if you have an asynchronous memory, or it could either otherwise build an asynchronous memory. Pause the video and think what's going to happen. Will this compile? Will it not compile? If it compiles, will it work? Let's first try and compile it. I've made this mistake before. I know what's going to happen. Depending on how much memory you ask it to use, how big that block RAM should have been, it may or may not be able to succeed. And I don't think it can succeed, because 512 bytes is too much to do another way. Let's see, what does it say? Replacing memory with BRAM with list of registers. Now, this is it warning you that you're a dingus. All right, right out of the gate, it tells you right at what it's going to do. All right. right? Now, I called my variable BRAM mem, okay, so that doesn't know I want to make a block RAM, but it knows I'm an idiot because I'm trying to create an enormous list of registers that's just ludicrously large. And it turns out it's not going to fit. If you let this go, it'll sit here for a long time, and it'll say, well, here's what I'm going to do. I'm going to make an asynchronous memory out of 512 times 8 LUTs. Well, I don't have that many. All right? It's not going to happen. What's it going to do? It's going to blah, 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 and then I'm going to try and do this. I'm inferring all this. It's making an asynchronous memory out of LUTs. And if we let this thing go, it's going to take a while to figure out how to do it. Come on. I don't know if it crashed. It should end with an error and it says I don't have enough resources to make that happen. Wow. I'm going to kill this because it's not ending right. Let me go ahead and just do this and let it scroll up on the screen so we can watch it go. Chug, 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 chug. It's trying to do it using a whole bunch of D latches. Did I do the math right in my head? If I want 8 bits times 512, that's a half of 8K. Oh, it might fit because we have 8,000 LUTs. It only needs about 4,000 to do this. This might actually run. This will be funny. But we're wasting, this is not the way you should do this. You really want to use a block RAM. It's really thinking hard about it. Yeah, see, this is the punishment you have to endure for making bad design decisions. So if this ever happens to you, you're probably not using the features of your FPGA in a manner that allows your compiler to infer what you meant. Because clearly what we really want is to use if we have block RAMs, it'd be nice to use them. And yeah, of course, you can do it the other way if you have enough LUTs and let it construct this thing, build a memory out of LUTs. Wow, this is just crazy. I've done this before and made the number too big and seen it fail. And it failed faster than this. So it's actually trying to really do this. Wow. So these numbers look recognizable. That's about how many bits there should be in that memory. It's a 4K bit memory. Look at all these gates and wire. It's taken it a long time to think about it. Oh no, timing analysis failed. And that's not shocking at all because it has to go through such enormous multiplexers and things like that in order to build such a memory. Wow, it's so much junk going on in here that it can't, it's not going to survive. All right, so that failed, and the only thing we changed is we changed it from a synchronous design to an asynchronous design. And yeah, this is just outrageous. All right. Now, it's also kind of weird since we're using non-blocking assignments and combinational code. But if you think about it, these things, I think I've mentioned this before, when we're talking about blocking and non-blocking assignments, these don't mean anything different when you're compiling for real. They make more of a difference when you're simulating. In fact, the only time they make a difference is when you're simulating. On a real circuit, these are the same as a regular old assignment, okay? In any event, this is what you want to do. This is your intention. If you don't use an edge to trigger a block RAM when you're supposed to use an edge-triggered enable or clock signal here, then the tool cannot infer the right thing, all right? So here's how you want to do this sort of thing. And you'll see it'll compile much faster now. In order to get what you want out of your system. Of course, I have to reprogram it, make prog. Let's look at the top file because I don't know if I fixed the other thing Yeah, it is. Now it should actually be working again. And I reprogrammed it, and it played its little game. It thinks it's still running, and it still is. So, and you can see it printed some garbage out right here. So it did glitch a little bit when it was rebooting. But, or not rebooting, when the FPGA was rebooting, it glitched a little bit. So we may have a weird situation with our CPU, but I did not reset the CPU yet, because just for fun, we're going to see if it still wakes up and is still able to run DDT after all that. Wow, that's crazy. So now we have, before we rebooted it, you could see it counting. Before this, you could see that I filled it with ampersands, as you might recall. Okay, and now we rebooted it. We rebooted the FPGA. I gotta make sure I'm clear about that. We did not reset or reboot the CPU. Okay, we're still sitting in DDT, and now we have all zeros in here. You know, you might ask, why didn't the ampersands come back? Because the ampersands, remember, when I first stored them in there, were stored in the block RAM in the FPGA. And we have reset the FPGA repeatedly, not necessarily the CPU. So it turns out the block RAMs apparently are all filled with zeros after they're programmed and you boot up the FPGA here. All right, so if I now, just for safety, let's reset the CPU to make sure everything's copacetic. No need to take unnecessary risk and confuse myself any more than I already am, right? So now if we do this again, we probably get the same results. Yes, you can see all the zeros in there from 200 or 8,000 to 82FF right there, okay? So now we should be able to fill and do something else. Maybe we can do 7 E or F, you know, I don't know, 80 through 81FF with, I don't know, how about a 54, whatever that is. Car 54, where are you? And then go back and dump the whole range, because I'm changing these numbers to change what I actually write into to see what happens here. So what did I do? I filled it to 81FF like a dingus. I wanted to leave some here that I didn't fill in, and I only backed off the 1 byte, okay? So anyway, the T's here, the 54s, exactly fill the block RAM. And I started it a little bit early. Oops. What I'm clicking on here. Did I start it up at 78? 7F80, yeah, that makes sense. That's what I started it with. And when I dumped it out, yeah, we can now see all this fun stuff. All right, so and basically it's working, okay? I'm interacting with it, and I can fill it, I can dump it out, if this is really what you want to do. And the idea that I have with this, by the way, the reason I'm doing this, is at some point I may want to do something like have a way to directly access memory on a video controller or something like that, as I'm dabbling with the idea of adding some video to this project, the Nouveau project that has this FPGA on it. And it would be nice to be able to just write into memory, you know, characters, letters, and numbers that might want to be on a terminal screen or something like that, and directly access it using memory. On the other hand, the Z80, even the S180, can only really access 64 at a time, 64K bytes at a time. And if you have a big old memory for your video, if you have 16K or 32K of RAM in there, which is not a lot of memory for video, right? It might take up an awful lot of your processor. So one way to do this might be that when you're dabbling with your video, you can temporarily turn on access to one of these memory banks, just like I have this one. This one's wired permanently in use, but the only thing I would have to do to make it temporary is to create an I/O port with a latch, for example, that would turn on and off the a bit. If we look at top V, so instead of letting this run all the time, what I could do is change these signals and say I'm only going to read from the BRAM when I want to do this, and the memory's in range, and add over here, and an enable bit is on in some GPIO register, which I can hook up like one of these registers. the flash, whatever, the GPIO output. I could put a bit in this register or create another register would be a better idea, so I don't overload what's going on with this I/O port. I can have an F2, and I can put a bit in there that could turn on and off this window down here to say, now the memory in this range is going to be giving me access to this block RAM. And then I turn off the bit, and this becomes inaccessible to the CPU. However, the memory would still hold its value. It might continue to be useful for other things while it's not mapped into the CPU address space. While the CPU, when it's accessing this range of addresses, would go to the static RAM. All right, so you can play all kinds of games now, popping these in and out of existence and mapping them in and out of the main address space of your CPU and use them for whatever you want. Now, in this scenario where I say, oh, I might use it for video memory, what I might do in that scenario is not necessarily make it readable by the CPU, so that any video circuitry could be reading this on its own, and I don't have to have, two entities fighting over getting access to this read port. Now, that opens up a whole nother can of worms. That's a whole nother video, a whole nother idea in itself. But this is the sort of thing you can do. Maybe if you had a triple port memory, you could do something like that. Or if you had a different kind of an FPGA that had a dual port memory, but there were full dual port where you can read and write out of this port. Maybe the CPU could do that and read and write out of this port over here at the same time, that you could use an I/O device could play around with that, like a video controller or something like that. That would be cool too. Many ways to do, crazy things, creating any kind of I/O peripheral you want using this kind of a technique here. All right, so that's one way you can use these block RAMs and connect them up to our now synchronous bus that is on our Z8S180 project, or use them for whatever you want in another project. Thanks for watching. I'll see you next time.